I want to talk about acid-base indicators, so we're able to estimate the pH of a solution, and our success criteria is being able to use the acid-base indicator chart to predict the pH of a solution. So what is an acid-base indicator? You know one already. Litmus. Litmus paper is a commonly used substance that turns red in the presence of an acid and blue in the presence of a base. However, litmus paper is made out of a chemical that's actually called litmus, and litmus is an acid-base indicator. What acid-base indicators do is they change color when the acidity or the alkaline of a solution changes. Litmus is very commonly used because its color change range is about from 6 to 8. So it will turn red in the presence of most acids and blue in the presence of most bases. But there are other types of acid-base indicators that change color in different pH ranges and change into different colors as well. We have two major purposes for these acid-base indicators. We use them to mark the end of titrations, and we will talk more about titrations in our last unit. And we can use them to estimate the pH of a solution when we use multiple indicators in combination with each other. So, an acid-base indicator is always given a generalized formula. We can give them a full and proper formula, however, these are often complex organic molecules. It's easier to just simplify them. On the table that we typically use, the lower pH, the acid version of it, is indicated with H, and then IN is a generalized form of indicator, and you'll see that in a second, whereas the higher pH is indicated with the IN minus. These indicators exist in equilibrium, so they can shift around which version they are, if they're the more acidy version or if they're the more base version, as their environment changes. Now, it's easier to explain this if we actually take a look at the chart. So this is the acid-base indicator table that we have in our Chemistry 30 data book. This is what I mean about having two different versions of the indicator. On the left-hand side, for like methyl violet up here, we see that its suggested formula is HMV and MV minus. If we look at chlorophenol red, we see it's HCH and CH minus. These are just indicating two possible ways of writing out this indicator. After that, we see that we have a pH range column right here. What the pH range column tells us is the range at which this chemical is going to change colors. It also tells us the color changes as the pH increases. So in the case of orange 4 is this column right here, we see that the pH change range is 1.4 to 2.8, and it's from red to yellow. That means if I put orange 4 in a solution with a pH below 1.4, it will have a red color. If I put it in a solution with a pH above 2.8, it will have a yellow color. Well, what if I put it in the middle, though? What if it's 2.0 for the solution? Well, what's between red and yellow? Orange. And that's actually where this particular indicator gets its name. The middle range for orange 4 is orange. All of these indicators work the same way. The pH on the left-hand side, below that, it's going to be the color on the left-hand side. The pH on the right-hand side, above that, it's going to be the color on the right-hand side. You'll also notice that we have this Ka. You don't need to use this in grade 11. In grade 12, when we talk about acid-base equilibrium, we'll talk about Ka values more, which is when we actually would be able to use these numbers. I also want to point out two of these compounds, cresyl red and thymol blue. Cresol red and thymo blue actually change color twice. Okay, the first color change for Cresol red is from red to yellow, and then the second color change is from yellow back to a different red. So it actually has two pH ranges, one for each color change. Same thing with thymo blue. It starts as red, changes to yellow, and then at an even higher pH will change to blue. This is okay. There are some indicators that change colors twice. You just need to um, use the information carefully with those. Make sure you're paying attention to both versions of thymo blue in order to nail down what the possible pH range is. The other thing I want to point out is that a couple, like phenolphthalein, have colorless as one of their colors. Colorless just means that it looks like regular water, okay? It's not that it's see-through. All of these will be see-through. It's not that it's transparent, it's that it lacks color entirely, okay? As well, if something has colorless as one of its options, like thymolphthalein goes from colorless to blue, what's the middle range going to be? Well, it's going to be light blue. It's going to be very faded, and then it will turn into a much deeper color if it reaches all the way to the end of its pH range.